Okay, so in the previous example, we looked at how changing the surface area of a solid can affect the rate of a reaction when reacted with a solution on top of it. But this time, we're going to look at the corresponding situation whereby we have two solutions reacting. So, for example, we could take hydrochloric acid and react that with sodium hydroxide and see how quickly those two solutions can react and how we can affect the rate at which those two reactions can occur. And what we'll again do is draw a particle diagram. We'll draw one particle of each of, we'll say, the hydrochloric acid for argument's sake. And then what we'll do in the first beaker is we will have a single particle of sodium hydroxide in there as well. And what you can see is that in order for a potential successful reaction to occur, the red particle of sodium hydroxide has to collide with the blue particle of HCl. And in the left-hand case, we can see that relatively straightforwardly. If we then do the same diagram, but this time just change the concentration of the sodium hydroxide, and in this case we can increase it. In this case, we can actually double the concentration. In surface area, it's not impossible, but it's quite difficult to control the surface area of a solid, especially if you're using a powder or an irregularly shaped piece of marble chip, for example. But the same situation can be quite easily achieved if you have a solution and you affect the concentration, because it's quite easy to use, for example, a 1 molar solution of sodium hydroxide compared to what we have now, arguably in this situation, is a 2 molar concentration of sodium hydroxide. Again, arbitrary numbers, but we can see that we've now got twice as many particles in the second diagram as we had in the first diagram. And so what this then allows us to do is see that there are now twice as many possible collisions. And if we can increase the likelihood of a collision, as we've said, if we can increase the likelihood or the probability of a successful collision in a given period of time, so number of collisions per second, then we can, by correlation of that, lead that to an increase in the rate of reaction. Now, because we've put a doubling of concentration and we've put a increasing of rate, it is possible in some situations that we can see a doubling of the concentration actually leading to a doubling of the rate of reaction. By increasing the concentration, we can actually now put a quantitative argument into this and actually now see that if we increase, or if we not only increase the concentration, we can now increase the rate of reaction, or increase the potential rate of reaction by increasing the potential number or frequency of collisions per second within that environment. And in the next example, we'll go on to look at how temperature can affect the rate of reaction as well. And that then we'll look at collision theory, and then we'll start to introduce something else called activation energy, which will again underpin the previous two examples as well.